Okay, this is a video 2, still day 1, Chem 1, talking about the mole, a measurement of matter. In our last video, we were on this paper, and we had talked about ways to count matter. We talked about Avogadro's number, 6.022 times 10 to the 23rd. We solved some practice problems, and we should be right here, the mass of a mole of an element and a compound. So we're going to switch our discussion over and start talking a little bit about masses. So quantities of matter measured in grams, to be specific. To do that, we need to backtrack just a little bit back to when we first learned that the periodic table gives us 2 pieces of information about each element. So I'll give you an example. Let's talk about fluorine, for instance. And if we go to the table, we see 2 numbers. The top number, which is the atomic number, 9, tells us the number of protons, but because this isn't a neutral atom, it indirectly also tells us the number of electrons. But that's really not what we're interested in today. The number we're interested in is the atomic mass, which is the bottom number, and for fluorine it's 19. Now this is a combination of the 2 heaviest particles in the atom, the proton and the neutron. Because they're the 2 heaviest, they account for the majority of the mass. The electron, while it does have mass, it's much less massive than the proton and the neutron, and so its mass doesn't really influence the overall mass of the atom. Now, when we first learned about this, back when we were talking about things like isotopes and average atomic mass and things of that nature, we learned that this number had a unit attached to it. We talked about it briefly, and that unit was AMUs. It's an acronym, of course, and it stands for atomic mass unit. We kind of left the discussion at that, never going much more into detail about that. But at this point, we need to talk about the fact that this mass number, 19, also has a different unit, and it's a unit that's much more important to us now in this chapter. And that is that the second unit is grams per mole. And so what that means is if we had, if we were looking at fluorine, and his atomic mass, now we know instead of reading it as AMU, which is still perfectly acceptable, we can also read it as 19 grams per mole. Now the other way to write that would be 19 grams per 1 mole. So what does this really mean? Well, it really means if we had 1 mole of fluorine, it would have a mass of 19 grams. And it's as simple as that. If we had more than a mole of fluorine, its mass would be more than 19. If we had less than a mole of fluorine, its mass would be less than 19. And we can, of course, figure that out, which we're going to do in a few minutes. So this new unit leads us to kind of a new vocabulary word, in that this is now not only referred to as an atomic mass or atomic weight, but it's also referred to as a molar mass. Molar meaning the mole part of the unit. So I'm going to be using that term quite often in this discussion instead of atomic mass, that we're going to be talking about this idea of molar masses. Okay, so now let's do some practice with molar masses. So going to the table, we can find molar masses for any atom, and so that's pretty simple. I expect that you shouldn't have any problem if I ask you to find, say, the molar mass of helium. You shouldn't have any problem going to the table and finding that helium's molar mass is 4, and of course now we know it has a unit attached to it of grams per mole. Okay, so that's very simple. What we're really interested in now is the molar mass of a compound. And so we'll do a few examples. Okay, so what do we do, for example, if we're interested in finding a compound's molar mass, say H2O? Well, if we go to the table, H2O is not on the table because, of course, H2O is water and it's a compound made of 2 hydrogens and an oxygen. So to find the molar mass of a compound is a very simple idea of adding up all the atoms' molar masses that are within the compound. So it goes something like this. Since I have 2 hydrogens, if I look at the table, hydrogen's molar mass is 1, but I have 2 of them. So effectively that's 2 times 1, or 2, and that's the mass of just the hydrogen part of this. But then if I think about the oxygen, if I go to the table and look up oxygen, oxygen has a molar mass of 16. So if oxygen's molar mass is 16 and the 2 hydrogens together have a molar mass of 2, to get the total molar mass for this, all I have to do is add them together. So of course, water has a molar mass of 18 grams per mole. And it's as simple as that. It gets a little bit more complicated as our molecules get bigger, but we'll do a few easy examples first. So a second one, how about SO3? Well, if I go to the table, I see that I have 1 sulfur, and sulfur's molar mass is 32. And I see that I have 3 oxygens, and so each oxygen has a mass of 16, so that's 3 16s, or 3 times 16. And all I do is add those together. So if you want to do this in 2 parts, and 3 times 16 is 48, and then adding the 32 to 48 should give us 80. Again, units are really important here, and this is 80 grams per mole. Meaning that if I had 1 mole of SO3, 1 mole of SO3, it should weigh 80 grams. That's what molar mass tells us. Let's do a third example. I'll put this one up here and then let you work on it by yourself just for a minute. So how about this one? According to our last chapter, we know this is the correct formula for magnesium hydroxide, Mg, and then in parentheses OH, because I need 2 of those. So take a minute and see if you can calculate the molar mass for magnesium hydroxide. Okay, so we are calculating the molar mass of magnesium hydroxide. All right, so I have 1 magnesium, so magnesium's molar mass is 24 plus. Now you can do this 2 ways. If you want to think about it in terms of single atoms, then you have to think about the fact that this 2 applies to the oxygen, but also to the hydrogen. So I have 2 oxygens and I have 2 hydrogens. So if that's how you want to think about it, that's perfectly fine. But that means I have 2 oxygens that weigh 16 and I have 2 hydrogens that weigh 1. So 24 and 32 and 2. 24 and 34, which means my molar mass is 58, don't forget your units, grams per mole. Which again means that if I have 1 mole of magnesium hydroxide, I would have 58 grams of magnesium hydroxide. Okay, and let's do one more. We'll make it a little bit harder. How about this one? Aluminum sulfate. Okay, so first of all, we'll have to have a formula before we can do a molar mass, so I'll give you a minute to write the formula, and then we will talk about how we can solve this. Okay, so if we remember from our last chapter on formula writing, this is an ionic compound. Aluminum is a metal and sulfate is a polyatomic, which are two indications that this is going to be an ionic compound, and so we have to deal with charges. So when aluminum becomes an ion, he loses 3 electrons, he's +3. Sulfate, it's a polyatomic. Your hint here is 8, not being found on the periodic table, and that's SO4 - 2. If you are doing it the way I taught you, you have to have the same number of positive charges as you have negative charges, and so we talked a lot about the least common multiple of these two numbers is 6. So I would need a +6, and I do that by getting 2 aluminums, and I would need a -6, and the only way for me to get -6 is by having 3 groups of sulfate, which leads me to a formula of Al2, and then 3 of these, and the only way to let your reader know that is to put that whole thing in parentheses with a 3. So there's my formula, but now I have to do a molar mass. So I'm going to erase this just so I have some more room. Alright, so my formula was Al2, SO4, 3. Now again, there's multiple ways to think about doing a molar mass for this. The first way I'm going to do it is a single atom approach. So I have 2 aluminums. Aluminum's molar mass is 27. I'm going to add to that the fact that I have 3 sulfurs, so we're distributing this. Sulfur's mass is 32. And I have, don't mind my dogs, they're at the door trying to get in. I distribute my 3 here, and I have 3 times 4, which is 12 oxygens. So 12 times 16. So this is obviously kind of a big molar mass. I'll just do it in parts. 2 27s are 54. 3 32s are 96. And 12 16s are 192. So add those together. And I got 342. Again, don't forget your units. Grams per mole. So again, meaning if I had 1 mole of this compound, I would have 342 grams of aluminum sulfate. Okay, what's the other approach to this? The other approach is to think about it in parts. The metal part and then the polyatomic part. You're going to get the same answer, but there's always multiple ways to do this, and I want you to be aware of that. So 2 aluminums, still 2 27s. Then the other way to think about this is 3 groups of SO4. So 3 times whatever SO4 weighs together. So sulfur is 32, and then 4 oxygens are 4 16s. So if you think about it like this, that works just fine. This gives you 54 plus 3, well, 4 16s are 64, and 32 and 64 is 96. I've just added those together. So I have this, 54 plus 3 times 96, which is conveniently 342 grams per mole. And so you see we arrive at still the same answer as we did just a minute ago with a single atom approach. Neither answer is more correct than the other, or I shouldn't say answer. Neither approach is more correct than the other. Both are fine. It's just all in how you think about it. So that's molar mass, and that's how we calculate molar mass. But now the question is, well, how do I use this idea of molar mass in converting? Okay, so if we flip over on our paper, we should have just finished this section, the mass of 1 mole of a compound or element, and now we're on this side, the mole mass relationship. Okay, so the situation here would be, what if I had a problem like this? Oh, let's see. What if I had 3 moles of NaCl? I want to know how many grams that would be. So again, this is going to be a dimensional analysis problem. They're all going to be dimensional analysis problems. So I'm going to set it up just like I set everything else up before. So 3 moles of NaCl. Draw my crossbar, put it over 1 if I want. And I don't want my moles, so I'll put them on the bottom. And I'm trying to get grams. So my setup looks just like this. Now, and my moles cancel, of course. Conveniently, we just learned about a quantity that has the units of grams per mole, and that quantity is molar mass. And so you're going to have to do a molar mass calculation here. So for NaCl, I have a sodium whose mass is 23, and I have a chlorine whose mass is 35. And so that gives me a molar mass of 58. Again, remember, 58 grams per mole. So for 1 mole, I have 58 grams. And now I have a very simple math problem. 3 times 58 gives me 174 grams as my answer. If we're being picky here with sig figs, I only have 2, which means this can only have 2. And so I would have to round that to 170 grams. Remember, this 0 here is not significant. And so my only significant figures in this are the 1 and the 7. Okay, let's do another. How about if I have 10 grams of sodium sulfate, I want to know how many moles I have. Alright, so the same approach is used here. I start with my 10. Oh, let's make this 10.0 so that way I don't have just 1 sig fig that seems like not enough. So now I have 3. Alright, so 10.0 grams of Na2SO4. Put it over 1. And I would like to get rid of my grams and change to moles. So, grams on the bottom so that I can cancel, moles on the top. Now notice this is still a molar mass. It still has units of grams per mole. It's just essentially flipped upside down, meaning that it's going to kind of go into the conversion factor differently than in our last problem. But I'm still going to have to calculate a molar mass for this guy. So I'll jump down to the bottom. I have 2 sodiums whose mass is 23. I have 1 sulfur whose mass is 32, and I have 4 oxygens who each have a mass of 16. So I add all that up together. I believe that gives you 142. Again, it's grams per mole. 142 grams per 1 mole. And so when we go to my chart, or my problem, I guess, 1 mole contains 142 grams of sodium sulfate. This time it's a division problem. 10 divided by 142 gives you a lengthy decimal. Something like that, and it even continues to go. But I'm limited here in my answer to 3 sig figs because of this. So round this to 3 sig figs. Remember, leading zeros is never significant. So right here, 704 moles. And there's my answer. So we can use molar mass as a way to convert between moles and grams of a substance. All we have to do is calculate a molar mass and then set up a dimensional analysis problem. Okay, now let's go one step further, and now we're going to go to the bottom section of your notes, mass-mole particles relationship. And this is where we kind of put all these ideas together and life gets a little bit more complicated. Okay, if you don't already have this paper, I call it the roadmap. You're going to get very used to seeing this paper here very soon. If you don't already have this, please make sure this gets passed out so that all of the students have this paper. If you already have it, then we're good to go. Okay, so let's say that I have a problem like this. Oh, let me make one up. I have 650 grams of copper. And I want to know how many atoms of copper I have. All right, so let's go to this roadmap for just a second. This is, in my opinion, the easiest way to teach this, and it's a visual representation of what we've been learning, and it gives you kind of a reference to go back and forth between. So I'm going to try to zoom this part in so you can see it. All right, so this is silly, but it's my way of trying to paint a mental picture in your head. So what this is trying to show you is we're gonna compare this idea to traveling and to traveling between towns. And so my 4 towns are these kind of grayed out areas. Okay, one is Grahamville, one is Moleville, being obviously kind of silly, one is Particle City, and the other one is Volumeville. Now we've talked about 3 of these already. We've talked about grams, we've talked about moles, and we've talked about particles, atoms, and molecules. We have yet to talk about this, but it will come into play later. Okay, so when we first started this idea, we learned about Avogadro's number, which, if you can see it, is right down here as kind of a little road sign on my map. And Avogadro's number shows that it connects Moleville to atoms and molecules, Particle City. And vice versa, it connects Particle City to Moleville. So meaning, if you're given atoms and you want to find moles, or if you're given moles and you want to find atoms or molecules, you're traveling on this section of the road, and you must use Avogadro's number, 6.022 times 10 to the 23rd. Now, with what we just learned, moles going to grams, or grams going to moles, notice it's a completely different part of the map, and it has nothing to do with Avogadro's number, who's over here. It has everything to do with molar mass. And so if you're changing between grams and moles, or moles and grams, you will use molar mass as your conversion factor. Now, let's look at our problem. 650 grams of copper equals how many atoms of copper? And this is where the roadmap comes into play. So, if we use it, I'll always ask you, where are we starting? And if I look at my problem, I'm starting here, 650 grams. Well, that means I'm starting here in Grahamville. And then I always ask, well, where are we going? And obviously we're going to atoms, which is Particle City. So I need to get from here to here. Notice there is no road that connects them directly. There's no road right here. There's no bridge. Okay, there's no way for me to get from Grahamville to Particle City without going through Moleville. So this is going to be a 2-step problem. It's not hard, it's just a 2-step. So we're going to first have to take our grams and change them to moles, and then take our moles and change them to atoms. And I know that because I'm using my roadmap to help me. So let's do it. Grams to moles first. Using, again, if you forget, come back to this, grams to moles using molar mass. It's right there for you. So 650 grams of copper. I want grams to go away, and I want moles to be my answer. So I go to my periodic table, I look up copper's molar mass, and I don't have to add anything because this is just a single entity, and I see that his mass is 64. 64 grams per 1 mole. If you haven't caught on yet, there's kind of a trick to remembering this, and that is that the number that goes with mole is always 1. And so if you kind of remember it like that, you'll never get these backwards. Okay, my grams will cancel and I'm left with moles. Now we could stop and calculate that here, but I'm going to keep going. But if we did calculate, we would have done this. Grams, used molar mass, and now we're in Moleville. And that's great, but that's not what my problem says. it wants atoms. So I'm here in Moleville, and I must make the jump to Particle City. So I don't want moles anymore. Moles will be on the bottom. And this time I want atoms. Using my trick I just taught you, this is going to be a 1. And if you question what the other number is, use your roadmap. Moles to atoms using Avogadro's number, which says that there are 6.022 times 10 to the 23rd atoms in 1 mole. Now my moles cancel. Notice I'm only left with atoms here. That's going to be my surviving unit. And now I do the math. Now there's a couple ways to do this. I tend to read left to right, so I tend to do 650 divided by 64 and then multiply that by Avogadro's number. But you can also do the top and then the math across the bottoms. You could also do 650 times Avogadro's number and then divide that answer by 64. Either way should give you the same answer. To 2 sig figs, and I got 6.1 times 10 to the 24th atoms of copper. Okay, let's do a second one. I've lost my eraser. Hold on. Oh, I have no idea. There it is. Okay. All right, let's say I'll make one up again. Let's say I have 7.25 times 10 to the 24th molecules of H2O, and I want to know how many grams of water I have. All right, so we're going to use the flowchart. Where are we starting? Well, they gave us molecules, and so we must be starting over here in Particle City. And where are we going? Grams. So Particle City to Granville. Now, again, there's no direct route, so we must pass through Moleville first and then go to Granville. So particles to moles, moles to grams. So particles to moles. I write down my number. I can put it over 1. Molecules to moles. Again, using the trick, 1 mole. In 1 mole, there are 6.022 times 10 to the 23rd molecules. My molecules cancel and I'm left just with moles, but I'm not done. If I calculated here, I would be in moles of H2O, but that's not what my question's asking. They're asking me for grams, so just continue it. I want moles to cancel. I want my answer to be in grams, so my moles cancel here. 1 mole is how many grams? Well, that's molar mass. 2 H's, each give me 1, so that's 2 plus 16 from oxygen, so that's a molar mass of 18. Notice the only unit that survives is grams, and again, I do my math. Again, I read left to right, so I take this divided by this, and then times this number, but you can do it either way. Be careful that you're not making any kind of calculator error, because that will give you a wrong answer. To 3 sig figs, I got 217 grams of water. Okay, so I want to do one more, and you might be asking what this little section is. It says atoms to molecules if needed, and so I want to show you one like that. And this is the hardest one that you would ever be asked to do. All right, let's say I have 250 grams of CO2, and I want to know total atoms. Okay, so let's go to our roadmap right away. They gave me grams and I want atoms. So I'm starting here in Grahamville. I must go through Moleville and then Moleville to Particle City. So again, kind of following the road, grams to moles using molar mass, moles to particles using Avogadro's number. So 250 grams. Grams on the bottom, so they cancel. 1 mole, this is molar mass. CO2, let's see, carbon is 12 plus 2 oxygens that are 16. That's 32 and 12, 44 grams per mole. So this is a 44. If I were to calculate this right now, I'd be in moles, but that's not what I wanted. Although that does bring me to here on my roadmap. Now I'm going moles to particles. Okay, so you might be tempted here to say moles to atoms. And that in 1 mole, of course, there are 6.022 times 10 to the 23rd. Now, that's actually a false statement. And it's only false because if you look at what we were given CO2. And CO2 is not an atom. It's made up of atoms, but it's a molecule. So when we take our moles and go into our particles, we're converting into what we call representative particles. And for CO2, the representative particle is the molecule because that's what CO2 is. And so in this case, this is not atoms, this is molecules or groups of CO2. And so if I were to stop here and calculate right there, that would be the number of molecules of CO2, which would essentially look like this. You know, some number, X, of CO2. Okay, some number of CO2s floating around. The problem is, that's not what this question asked us. They wanted to know total atoms in a molecule. Well, if you look at your formula, you see that for every 1 CO2, there are 3 atoms that make it up. There's a carbon and there's 2 oxygens. So for every 1 molecule, there are 3 atoms. So for every 1, oops, forgot to cross out my moles. For every 1 molecule, there are 3 atoms. And so that is going to give us our total atoms in 250 grams of CO2. Again, this is the hardest one you'd be asked to do, but this is where you're given a molecule, but you're asked about atoms. And so you must go that last step. Let's see what we get. To 2 sig figs, I got something along the lines of 1 point, well, it would be 1.0. 1.0 times 10 to the 25th total atoms as my answer. Again, if you're doing it like I do, 250 divided by 44 equals, if you're using my calculator, and then multiply by Avogadro's number, and then multiply by 3, and you should arrive at this rounded off to sig figs. So these problems in and of themselves aren't exactly difficult. They can be a little bit confusing, but that's why you have the roadmap. Okay, that's why you have this to kind of guide your thought process. It has the conversion factors written on there, and all you have to do is understand how to read the roadmap, and you should be good to go. Now, the one question you should be asking is, well, what's this whole deal with Volumeville? And that's a lecture for another day, but we will get there eventually.